rope. It can be both of them be on a flat horizontal surface. One can be on horizontal and one be hanging. And then the one hanging should be hanging vertical, or maybe it can be both on an incline, and then there will be a stream maybe or without a friction or with a friction. And then one can be the one that we are having both hanging. And then let's talk to this last one. Let's talk to the direction, because as it is hanging, one when it is going up, the other one it is going to go down. So these are the scenarios that we are having. But when we address them, we have to take each object separately. Hence, the question will be saying, draw the free body diagram. On one, they are going to mention one, and then they need to relate it to the other object. So it is important that we encourage our learners to draw the vertical, the free body diagram for both, even though maybe in this case, they will be asked on one to draw, but for the calculations, they need at least to draw the two. The other thing about this question that we need to remember, it is that on an incline, for free body diagram, we are, in fact, in all, we are not going to accept the weight, the components of the, we only accept a weight on the free body diagram, not the components. But for calculations, we encourage our learners to can come up with the components on the calculations, but not on what we are having here as a free body diagram. Now, the other thing that I want us to look at, it is this one here. Right, now, where do we get the marks? It is going to be, I'm moving to vertical projectile because my time is not on my side. It was just an hour, so I'm going to rush. So I'm not going to say I'm going to end up, but we'll talk to it. So, sorry? Okay. So with vertical projectile motion, now where do we go? Like I indicated with the forces, with Newton's laws, when you go to the data sheet, we are going to concentrate more on the way it is written forces, but guide them. That even though on the data sheet it is all about the forces, part of it is on question number 4, because we are having momentum project, in fact, formula is there. So we need to look into that one also. Now, when you are coming to this one, colleagues, for vertical projectile, I want us to be very careful about one thing, that if we are having a vertical projectile, let's go and try to draw a table like the one that I'm trying to draw. In that table, please, let's check what is happening. G, it is not going to be given to our learners. So there must be at least a value for G, which they can read from table 1, which is 9.8 meters per second squared. G is not going to be given. But immediately, when they read the statement, then it will be saying maybe a ball is thrown vertically up. Now, they are going to say it is vertically thrown vertically up, it is initial velocity, and then it is having a value. Let's say it is 15, for instance. It's 15 meters per second. Now it is going up. Now it is at this point where now they have to decide about the direction. Now, what else it is there? Now, if the question says they have to calculate maybe the time. Now, time, it is going to be an unknown thing for them. So it is going to be unknown to them. What else it is there? Now, it is time to the maximum. The learners, they should be knowing by now that at the maximum height that the object will be reaching, your V final, it is going to be equaling to 0. Now, what does it mean? Now, here we are having 4 variables. Hence, here it is 4. Now, where do we use this 4 by 4? The 4 by 4, the other 4, it is for choosing the formula that it is having all these 4 variables at the same time. Remember, if they're not doing, they're not calculating, or they're not using the formula as it is, containing all these 4 variables, and then they're going to do another calculation. The danger is if they are going to miss out or maybe make a mistake in the calculation of the first one, it means these learners are changing what was not a multi-step equation to a multiple step question. So they commit a mistake. Now what is going to happen? Now when we mark, usually now of late, we are marking a formula leading to the answer. So they'll only get that 1 mark, and then they're going to lose any mark on the substitutions. And then therefore, because the substitutions are wrong, then they are going to lose a mark for the formula. So if it is not a multi-step type of a question, and then they turn it to be a multiple choice, a multi-step question, then it means they are going to lose all the marks, and then they are going to get at least 1 mark. So this is not what we want. So let's encourage our learners to use this strategy of 4x4, that we are having 4 variables, and then in that 4 variables, then they must choose a formula which is going to contain the 4. And then the formulas that they're using, let's encourage them. We are having 4 formulas there, but let's discourage them to use the last one, where it is 7 delta y equaling to v final plus v initial over 2 multiplied by time. Because our learners are committing a mistake there also, that instead of putting a plus, they are putting in a negative sign that makes it a change. And once it is like that, then our learners will get a 0 because it's a wrong formula. We are not saying it is a wrong substitution or whatever. It is a wrong formula, and by principle, it is going to be 0 out of 4. This is how we look at the formulae. Now, the same thing will happen even for the 2 objects. When we are having 2 objects, that means they need to take each object and get a formula for each and try to relate it, because if it's a 2, it means it is going to be a simultaneous type of a question, and then they need to talk to the relationship between the 2, how it is going to be related, and then they'll come up with whatever it is there. Now, the other thing that it can be asked here, it is, let's encourage our learners that if they are saying, the statement is saying something, let them try to draw the trajectory for that object if it is a 1 object, or a trajectory for the 2 if we are having 2 objects. And once we have that, then it means if they can draw that trajectory, it means, for instance, a body will be vertically up. As it is thrown vertically up, for instance, it is thrown vertically up. No, that one is too heavy. Let's take this one, small one. So we are having something like this. This is a trajectory. Now, to throw a body, usually you don't throw a body from the ground. We are throwing it vertically from a certain height. Then it is going to go up and then reach a smart and then go to the ground. Now, immediately the learner have drawn this. In essence, this is what it is happening. Now, along the y here, this part now become their initial velocity, initial height. This is going to be their initial height. So they can read this height here. They can read it there. And then the other thing, you can see now, because it is the height and then it is taking this, then automatically it makes this side to be our time axis. It makes it to be our time axis. Now, when they are to draw the displacement time graph for this, then this will suffice, because now they can get to tell us that this time here, it is going to be the time it takes to reach the maximum height, because it is at that particular point there. So by drawing the trajectory, ultimately you are going to get a velocity time graph that it is happening here. So it is very important that we get this one correct. Hence, it is important that they draw the trajectory, because it is going to help them to can draw the displacement time graph. And then the other thing which is happening here that we need to take care of, it is the issue of how do we calculate when given the graph, how do we talk to the area? Let's talk to that, you know, sometimes when we're having a velocity time graph, when you talk of the area, here's a velocity time graph, for instance. Now we are having this velocity time graph. Now, to our learners, we say under. Here it is under the graph, it is fine because it is there. But when reaching this point, some of the learners will be coming and put this point. So let's avoid to use the word under, but instead let's take and say it is the area between the graph and the time axis. Why? Because the graph it is here, the time axis it is here. Now the area it is going to be about this part here. And when we come to this side here, because we are having this area here. Now, this is the area between the time axis which were there and the graph was here. So we are talking about this area here, not this one here, because this is not the area under the graph. So the way we are talking to the areas and whatever we are having, then let's try to talk to this area under the graph, not under the graph, but the area between the time axis, because we are directing them that it should be between the time axis and the graph. Then it is going to be easier for our learners not to lose mark, because immediately it goes here, then you'll be calculating something here which is going to be like a trapezium or whatever, then it is going to be a wrong thing. And then also let's talk about this. Immediately your trajectory, we can see maybe from here that your trajectory, it is saving this point until this. Now at this point here, it is traveling longer than it takes there. So the area of this area here, it should be smaller than the area reaching this part, because it is representing all this part here. So when they draw the graph, they must also talk to that part, and then thereafter, then we know that at least we are talking to the correct thing. And then with the bouncing balls, they say, colleagues, that as it is bouncing, then they need to talk that it is hitting the ground, go to the maximum, come back to the ground, and then talk to the lines as being parallel. And what is represented by those lines which are parallel? It means it is parallel because the lines are under the same thing, that they are only force acting there, it is gravitational force. So it is the same force that it is acting there. So we don't need to redraw that graph. And then for that graph, if maybe it is asked colleagues to draw the accelerating time graph, we draw acceleration time graph as a single straight line. Why? Is because we didn't say, we are saying it is still, even though it is bouncing, it is still subjected to gravitational force, and then the gravitational force, it is not changing. So maybe let's refrain from drawing this type of graph where we'll be saying then it is going to hit the ground, come back, and then start to come up with these sparks here. It is not necessary for us to draw these sparks. Instead, let's go and draw only one line, straight line for acceleration time graph. This is how we can go about when we deal with vertical projectile motion. I hope we are still okay, and then we are still following each other. I just hope so. Can I pause here and then try to find out if there are any inputs that you want to make? I shouldn't just present myself. Is it okay, colleagues? Colleagues, I'm still in the meeting or not? Colleague, can you hear me? Are we still fine?
Yes, sir.
All right. And the presentation is still visible to everyone. Okay. Right now, colleagues, when talking about the graphs of those two, now we are having this thing where our learners, they still need to draw the vertical projectile graphs. It can either be a velocity time graph or it can be a displacement time graph. Now, it is important that we relate what we have with the velocity time graph. Let them use this equation here for that one. And then this equation is also helping the multiple choice question, because if you are looking at this, V final equal to V initial plus G delta T. If we rewrite this equation, because they are all positive, then we can start with G delta T plus VI initial. Now, because it's a straight line, that means we can put it in the form of Y equaling to mx. Now we need to talk it that the initial velocity, it is actually the c. That's why your graph, it is cutting the y-axis. From their mathematics, they will know that. And then the x-axis, it is where you are having your time, then it is going to relate to that change in time. And then the gradient of this particular graph, then it is going to be our acceleration, which is gravitational acceleration. So for multiple choice question, now this will help them to can say when they were asked, or maybe if they are asked what is going to be the gradient of the velocity time graph, then they can strictly say then it is going to be the gravitational acceleration. Now, for this motion, I've taken up as positive. but we can still do the same and take up as negative. Then it is still going to go the same. The only thing that is going to change, it is just that the gradient now will be changing, but the C will still be the C, and then the gradient is still going to be the gradient. Nothing is going to change for that one there. And then for the displacement time graph, what is happening is that for the displacement time graph, let us try and talk to this particular one where we are having a equation which is going to be relevant for the displacement time graph. In giving us the shape, it is going to be this formula here, that delta y it is equal to V initial delta t multiplied plus half g delta t squared, this one here. And then when we change this, because g it is negative, ultimately here it is going to be a negative 9.8 when we rewrite it. This will remain as positive, and then this is where it is happening. Now, based on this, now what does it tell you? It tells us that because the value of a here, which is the half g, it is negative. Now, from their point of mathematics, they know this is going to be a parabola type of a graph, which is an ugly shape. Why we are starting not at 0 is because our time can never be 0, can never be negative, not 0, can never be negative. Hence the graph it is starting there. And then the crucial point, it is this one here, that where it is cutting the x-axis, it is actually talking to the y initial, because from there we are having delta y, it will be equal to y final minus initial. Now bringing the y that side, it is going to be positive, hence we come up with this particular graph. So the shape of this graph, it is very important. Now this particular part here, the last part here, colleagues, it is very important when we are using scenarios where we are having a hot air balloon moving up and the stone is being thrown. Now, if the learners were to calculate the distance between the two, remember the hot air balloon, usually they were saying it is going to move at a constant velocity. So because it is moving at a constant velocity, it means acceleration will be 0. So then it means then it is going to be looking at where this balloon, it is going to be after whatever time that they were having. Now they're usually being given the time, but the initial velocity, if this is a point of reference, now this y will become 0. But for the stone that it is being dropped, now the initially it was here at 0, but now it is moving a particular distance down here. Now they can calculate what is the time here, or what is the displacement here, and then what is happening to the balloon that is going up. So we have to relate the two using this particular equation here. Then it is going to help us, and then we'll come up with the distance between the stone and then the hot air balloon. The difference between the two, or maybe the addition as a distance, it will depend on how you look at it. Then it is going to give us what is it that we want for that particular question. So this graph or this equation, other than showing us the shape of the graph, it is also talking to the distance at a particular time where it is. And then for us as teachers, remember, we were looking at this as a bullet that was added, but it was not added, it was just that it was refined, that now at that particular point, the y initial, we need to talk to the time at a particular point when the ball it is starting, or when the ball it is being projected. So it is going to give us that particular distance where that particular ball it is going to be. So it was just a refined type of a bullet, and not necessarily that the bullet it was new. So this is how maybe we should approach the vertical projectile. We go to the data sheet and our learners focus on the heading, because it's a vertical projectile motion. On the data sheet, we are having this clue that the equations of motion are under the topic where it is written as a heading motion. Then they can look at that, but they need to take care of the signs and what is going to be negative and what it is going to be positive. Right. So also here, colleagues, there is a possibility of graphs and there is a possibility of simultaneous equations if we are having two objects happening, or two objects under the influence of gravity here. So it is very important that we also look at simultaneous type of equations that can come up here. So possibilities of the high order questions are here, but we are not saying go and focus on them. Still struggle, maybe grapple up with the easier one for the learners so that at least they understand the basics before they can go to the complex. Let's go to momentum. Now, if you go to momentum and impulse, the possibilities are there also. We know there will be some calculations, but there can be also some graphs that are there. Then also on the impulse, colleagues, there will be an impulse momentum theorem. F net delta T equal to change in momentum. Now this one here, there is a possibility of a multiple choice question also here because of the rate, because of this delta T here, then there will be a change in momentum here, which is equaling to a change in momentum. And then we need to talk to this one here. But also, colleagues, on this formula, let us check what is it that it is happening. It is not on two objects. We have to concentrate on the change in momentum of the very same object that force is being applied to, because a force is applied on an object by another object. So we look at the force that is applied on the object. And then also we need to look at the safety consideration. And for safety consideration, the most important part, it is this one here, the change in time and the change in momentum, because at the as the force when you divide them. So the longer the period, then the lesser will be the force that it is going to be there, because for the same momentum, that's explanation it is coming in. We apply this, but we need to talk to the variables that the momentum for the test to be either high or low to cause the injury. But that is why it is important that we need to make our explanation based on the principles that we are having and look at the variables and such other things there. And talking to a closed system, but we are talking about then isolated system. And our learners, they need to understand what we mean by an isolated system. We are isolating it. That means we are removing all the other external forces, then we are left with that. So it is important that we look at that. And one of the forces, that is the reason why always when we address this question, they will be saying, ignore the effects of friction, ignore the rolling effects of the wheels, because these are giving us other forces that we don't need them. Now, also, we need to distinguish between elastic and inelastic collisions. And then for that, colleagues, please, we are not applying change in momentum. We have to apply the kinetic energy. And then let us not start with a conclusion. We need to have them either being equal or unequal for it to be elastic or inelastic. So our learners cannot start with a conclusion saying the kinetic energy of object A plus the kinetic energy of object B, it is equaling to the kinetic energy of object A plus the kinetic energy of object B after collision. Immediately they do that, it's a conclusion, and that is what we want. And then ultimately when they do the calculations, what they do now they start to cancel and make it not to be unequal. Now, because of that, now we are confused as to whether at one point it is equal, and then at the last point, only at the last moment, it is not equal. Now, then we have to penalize them. So we don't want the learners to lose any mark. So let them calculate separately the kinetic energy before, sum of kinetic energy before. It shouldn't be for one object because it's a collision of two objects. Now it must be sum of the kinetic energy before. So it is kinetic energy of object A plus kinetic energy of object B, and then being equaling to the kinetic energy after of object A and of object B. And then let's talk to that after, colleagues. The after means there must be something happening after the collision. Collision, it means these two objects, they were there. Now, after they have collided, what happened? If they are not colliding, then there will be no collision. So we need to talk to that collision also. What is it that it is happening there? I hope it is okay with us. And then the other thing which we need to look at, it is work energy theorem, which is going to be question number 5. If we are following the trend, let me say, if I am following the trend as it is throughout the years, that question number 5 is normally work energy and power. Now, what is it that it is happening? Work is done on an object. So because it is done on an object, now we have to treat, even if we are having two objects in the system that it is put there, we need to look at each object and identify all the forces that will be doing work on that particular object. Being it on horizontal or being it on an incline, we need to look at that. And then thereafter, we look at which it is doing positive work and then which it is doing a negative network on that particular object. Let us also talk to, especially when we go to work energy theory, that the W net, the net here, it is not only for one force, but it is for a combination of forces. Hence, we find that maybe then will be required to can calculate work done by friction, whereas there are other forces which were doing work. So it is important that we look at the net and try to explain it. And then also here, because of the change in kinetic energy, the kinetic energy, it is only on the kinetic energy of one object. We are not adding the kinetic energy of different objects. So it is very important that we look at to this. And then colleagues, when the questions say use energy principles, I will encourage our learners to stick to work energy theorem. As a theorem, it means it is applicable everywhere. Being it whatever, it is going to be here. Now, if we have this correct, then our learners will always get this one correct. Nothing is wrong with work done by non-conservative force. It is still applicable in each and every situation. Because the thing is, with the non-conservative force, they need to identify which non-conservative forces are there. And then we need to talk to the forces which are non-conservative. So those are the forces that are doing work. It doesn't mean because it's a force. When they define a non-conservative force, now they say it's a force. It is actually a force, a work done on that, but by that particular force that we are looking at. So we need to talk to the work here when we are defining the non-conservative forces there. So we need to look into that. And then please, colleagues, let us not overlook the power. So here on the power, the chances are about the windmill drawing water. So we need to talk to gravity. That's where the negative work it is coming in, and then the positive work it is coming in, and then we relate that. What is happening? Because we are drawing water, maybe, or we are drawing water, then that water will be having a mass, and then drawing up, it is going to be that, but gravity will always be doing work about that. But there will be that change in potential energy, which is there. That is why we need to do some examples also on the windmill. We cannot just overlook them. And then also let us look at where we are having average power. And then the average velocity there, colleagues, it is not just ordinary velocity, it's an average. So it is very important that we look at calculation for the average velocity before we can go and do any other. So it is important about this, that we look into that. And then the other part, it is all about Doppler effect. Colleagues, here with the Doppler effect, there is a possibility of a graph, or there is a possibility of simultaneous equation calculation. We are familiar with them. But what is important, it's about this formula here. Let's still encourage our learners to can write the formula first as it is before they develop it. What is it that is going to be asked? It is either the source will be moving or the listener will be moving, or the source will be stationary and then the listener will be moving. So one of them needs to be moving. There is no question where they will be both moving. It is out of syllabus. We cannot give it that. Now, because of the simultaneous, don't think they'll be both moving. It cannot be. One of them must be stationary and then the other one should be moving. So it cannot be both of them. And then let us not overlook the redshift. With the redshift, colleagues, it is typical to be a short question, but that short question, it is very important. Even if it can be 2 marks, that 2 marks, it is more than 1%. So our learners, just think of a learner who is at 73 marks out of 150. Or is it at 149 out of 300? So we are costing that learner at least a 1% that could have given at least a better level for that particular learner, or to pass at least physical sciences, if we look at it. So when we talk to this, colleagues, let us talk to the shift of the spectral lines. And let us not be maybe too lenient that now the learners will be shifting, the spectrum is shifting to the right end of the spectrum. It cannot happen. It is the spectral lines that are shifting towards the right end of the spectrum. And then we talk to what is happening, because it is red shift. Red, it is associated with a longer wavelength, which is going to be associated with a shorter frequency. So that means, because the shorter the frequency, from what we have done with the Doppler effect, the frequency becomes shorter or smaller if the object it is moving away. Because it is moving away, then it is evident enough that then the universe it is expanding. That is where the red shift it is coming in. And then blue shift is not us for now, but it is part of it, but we are still on the red shift. So for question number 6, we are expecting it to be a Doppler, and the possibility it is just the calculations of this, and then it can either be in a statement or as a form of a graph. So if a form of a graph, it can be something like this. It will be starting maybe up and then going a bit lower, or it can still, colleagues, start lower and then go up. So in this first instance, because it's starting up and then it is going lower, it means, therefore, in the first instance, it was moving away. But in this second instance, then it is moving towards, because now your frequency, it is becoming higher and higher. And then we move to question number 7. With question number 7, we are having two combination of two. It can either be strictly on Coulomb's law, and for Coulomb's law, we are having either in one dimension or it can be in two dimension. But when it is in two dimension, then that means we are going to have it, the charges be on the vertices of that particular triangle. So that's where the 3 will be coming in. Now we'll talk about the force here, and then we'll talk about the force there. And then from there, what is going to happen? Because these forces are reactive forces, Newton's third law will come into play. And then also here, it is important that the learners should look, if this is positive and this is negative, and this one also, it is going to be negative, they need to look at this, what is happening here. Now, if this, it is all about this charge here, which I'm going to say it is charge A. Now, charge A, it is going to be attracted towards this one here. So it means when they draw the vector diagram, then it should be going in that particular direction. But at the same time, this one is negative and this one is negative. Now across here, that means this force, then it is going to go in that particular direction. Now from the information of the vectors, it means therefore that then their resultant force will be in the middle of that. It is going to be a diagonal to that. So we need to talk to this part also. And also, colleagues, because it's a right angle triangle, now theorem of Pythagoras comes in, and then everything, we need to look at it across this. Important about this, it is when you look at the distance, because the charges are a small distance apart, that is where the conversions are coming in. So we need to come out very strong about the conversions here, moving from centimeters to meters. What is it that we are doing? Moving from decimeters to meters, moving from millimeters, whatever, we need to be coming very strong here. Also here, we need to talk to what we mean by nanometer, what we mean by micrometer, by picometer. All these here, conversions are very important. So the exponents are very important here, because immediately a learner misses out. If the question is talking to the nano and then it's writing the macro, that means that exponent it is wrong, and then because of that, the substitution becomes wrong, and then automatically the answer becomes wrong. So it is important that we look also at the conversions that are coming up with this particular force. The other thing about this, it is on the definition. Now, on the definitions of Coulomb's law, The same with the gravitational law. The two laws are all about the relationships that we are having. So our learners, they usually forget to write, about the product. They just say it is the magnitude. Now, because it is the magnitude of that, then it is going to be, then we minus 1 mark because they forget. I don't think it is they forget. I'm not having the authority to can say they forget. They omit the product because they omit a product, and it is one of the words that are going to be underlined. It means that particular learner is going to lose 1 mark. So we need to guard against those learners losing 1 mark here and there up. So we need to look up to that. Now, if it is not about Coulomb's law, it can be about electric fields, or it can be about the combination. So we need to move to the two. Now, when you go to electric fields, it is important that our learners, they draw the electric field lines. The patterns are very important. And colleagues, please go and revise this part of the electric field. The 3 marks, it's a lot. So marking the direction, marking that at the end, they are not symmetrical, they are caving, they are doing that. Take note of that and take care of them, that the learner shouldn't lose a mark about the curvature of the electric field lines. It is very important. What is it that we are having? We can have a radial one when we are having a single charge, but when we are having 2 charges, one negative or both being negative, or both being positive, or one being negative and one being positive, it is important that we also look at what it is happening across the field lines. So across in the middle and also on the edges, what it is happening. Those curvatures are very important to us. And then the other thing about this part here, colleagues, here it is where also the net it is coming in. So it is important that we look at the direction, especially when they were to look about the net electric field at a point. Now the direction will be coming in. And then this is where, if it is just 2, then they will be introducing at least another charge, it is in the middle, or an electron is being placed. Now, because if they're talking of an electron, it is important that we refer our learners back to can say, immediately they talk to an electron, make reference to table number 1 and check what is the charge of an electron, because they are going to get it there. But our learners are so fond of memorizing that they usually go and just put them. But it is actually because of us. We are taking it out of our head, and then we think our learners also are going to take it up by our head. So let's make reference to table number 1 of the constants also to can get whatever it is going to happen. Now, if we're looking below here, I'm having these 2 equations here. The first one that I've circled, it is talking to electric field at a point. So the calculation for electric field at a point, we usually use this one here. So it is important that the learners, they should know the distance, what is happening to the distance. That is where the conversion also it is coming in. The second one here, it is all about defining electric field at a point, because it is a force experienced by a unit positive charge. So this one, it is talking to the definition basically. So it is important that we also refer to our learners to the equations that are also giving us the definitions. So it is important that we coach them well, so that at least they can pick up any other mark which it is available for them, and then they will get it if we guide them correctly. So then let's move on to electric circuits and then check what is it that we are having. Now, with the electric circuits, colleagues, also there is a possibility of simultaneous equation. So we cannot just give straight away questions, but there is a possibility of simultaneous equations. Now, if a learner knows how to deal with the simultaneous equation in Doppler, then they shouldn't struggle with the simultaneous equations in in electric circuits. The same goes with any graph. If they can interpret any graph in vertical projectile, then they should be able to interpret the graph here of whatever it is happening. Right, so we are going to get those type of questions that we have. Now, when solving the problems using this equation here, colleagues, let us all strive or maybe help our learners to can say, before they can even attempt to answer the questions, they must try to understand that first, they need to trace the current. What is happening? And then encourage them to come up with 2 pence or so that if they trace a current and then at a particular point, they see now there is one path of the current and then another path for the current. That was initially a total current. It means at that point where they're having this should be spelling to them that we are now going to have a parallel combination. We are going to have a parallel combination. And then in the parallel, what is happening? Now the current, it is dividing. But to our learners, dividing means it is sharing equally. Just talk to not divide, better say they are going to share the current unequal so that at least they know what it is happening. And because of that, now they should be saying now Ohm's law comes into being, that now V for the parallel, it is going to be the same. Because V, it is the same. Now, R, it is going to be inversely proportional to the current. Now, let us try to talk to this statement, because this statement is a very important statement to can say, then that will be saying the way the current is going to split, wherever you are going to have a lower resistance, it is the one that it is going to go and get a higher current. And then this statement here, or this relationship here, it is very important because now it is saying to us that the current is very opportunistic. It's opportunistic in the sense that it takes the easier route every time. Hence, when you talk to bridging, remember in the bridging what it is happening. It is that the conducting wires that you are putting in the statement, it will be saying the connecting wires and the ammeter have negligible resistance. That's resistance which is very negligible. It's so small. It means it is going to allow all the current to pass through. Hence, in bridging, then all the current will go in one and not in the other. So that is very key that we talk to this statement for our learners. Even in the explanation, what is going to happen to the voltmeter reading, then this part here, it is a very important part that we need to talk to. Other than that, colleagues, please, let's ensure that even if we are applying the questions from textbooks and everywhere, the maximum of resistors that we can have, it is only 4. And then the 4 can be either parallel, all of it being parallel, can be series, or it can be a parallel and a series combination. So then that does not include, it doesn't include the internal resistance. Internal resistance is standing alone. So maximum of 4 means on the external circuit. And then also we need to talk to power. Now with power, basically, it is where brightness will be coming in. Now, when we reason brightness, colleagues, for the bulbs that will be having, we need to look as to whether is it parallel. Now, for explanation purposes, if it is parallel, what is it that it is going to be constant? Then we know that the voltmeter reading, it is going to be constant, or the potential difference is going to be constant. Now it means for parallel combination, your power will be inversely proportional to 1 over R. So the lower the resistance, then the lower the resistance, now there will be a higher power. Why is that case? Because all the current it is going to go through, and then the heating effect, it is going to come out. So where a lot of energy it will be coming out of that per time as a power. And then for the series combination, we use this one here, this equation here. Why? It's because the current in the series combination, it is the same. So your power in this particular case will be directly proportional to the resistance. So it is very important for our explanation type of questions to can relate these two equations to what combination are we having? Are we having a parallel or are we having a series combination for the learners to can get, and they talk to the total resistance and then they talk to the total power that we are having. Then we'll end up maybe with the marks that are required for us to can have. So this one is going to be for series, and then for this one we are going to use it for the parallel combination. So this is basically what we are going to have. And then when you go to the calculation of the usage, colleagues, now if you look at this, the kilowatt, it is actually the unit for power. And then this one, it is actually the unit of time. So basically from this equation, power as the rate of doing work, it means basically this, it is actually giving us the energy, the electrical energy. So it is important that whatever we are doing here, first, if the learners have calculated power, now they need to take it to kilowatts, convert it to kilowatts by dividing by 1,000, and then from there multiply by the cost, and then the time. The time should be in hours, not in seconds, like we usually do, because this is what we are using here. So it is important that we revise the grade 11 costing for us to can get this, because it is still going to be asked one way or another. I'm not saying in this paper, but it can be asked. I'm not an examiner. I'm just talking about what is it that it can happen to our learners on Friday. And then the next question is going to be about the machines. Now, with the machines, and then I'll refer you, ma'am.
Pele Uya Hood machines, we had 2 hands by Relebohile and Gift November.
Okay.
Can you please
Now
give
let
them-
me take the hands, ma'am.
Yes, thank you, Dad.
Okay, that. Yes, in that in November.
No, it was a mistake, that sorry.
It was a false mistake. Okay, it's fine. Mary Relebohile. Relebohile Mokhotu. Hello. Mesapi, can I move on? I don't get the response.
Yes, please, sir.
Okay, no, it's fine. All right. With the electrical machines and the vertical, in fact, not the vertical project, and the electric circuits, colleagues. With this one, let's emphasize the subscripts. They are very important that these learners, when they write these equations, they must have subscripts. All right. So the subscript must be there. And then the other thing about this, where do they get the formulas with subscripts from in this topic? They go to the data sheet under table number 2 and look under alternating current. Those are the formulas that they need to use. The rest of this, being it Coulomb's law, being electric circuits, the heading is talking to what is it that it is happening. So with this ones, it is going to be this. Now, this table, or maybe these calculations here, are not very difficult type of calculations that we have. But what is important, colleagues, on the motors, let us talk to that motors they use, motor effect, and then the generators that are using electromagnetic induction. It is not correct to say that the motors are using Faraday's law. Faraday's law, it's a Faraday's law of electromagnetic induction. So it is not really true that the generators are operating under Faraday's law. They are just operating under electromagnetic induction. And then also we need to talk to the energy conversion. Now, usually when I do this, I usually ask especially my girl learners to write the word right. Now write as right hand, and then I encourage them to write the G in the capital letter. So the right hand, it is for the generators in capital letters G. for the generators, so that at least they know what is it that they are using. And then the fingers that we are using only 5. We are looking at the 4th finger. Now it's starting with F for the magnetic field, and then the central finger for the current starting with C, and then the thumb for the thrust, which is the same as the 4. So these 3 fingers are very important, that it is for the same hands, but one it is for left and then the other one it is for right. And then for us as teachers, having cars and having seen cars for a long time, including the motorbikes, we know motorbike, motor car, they are moto. So moto, South African rule says we have to keep left. So that is the basic rule for us. So for the motors, we'll be using left, but for the generators, we are using the right hand. So this is how we use it. And then for the energy conversion, at the end of each, we need to get, maybe for instance, if it's a generator, we need to get electrical energy. That is how we start. But before we can do this, there must be a rotation. Now this rotation, it is all about mechanical energy. It is about mechanical energy. Now that mechanical energy that we are having, it means we have to start with it. Now when we start with it and go to this one, then we are talking about the generator here. It's a generator. But when we start with plugging something so that it then rotates, then we'll be talking about the motor. So this is how maybe our learners can use it and get to know the difference between the two and the energy conversion, which is usually a usual question that we are having. And then the fingers, they will be talking about the rotation. Is it going to be clockwise? Is going to be anti-clockwise? So those are some of the marks that our learners can still get, and then we look at them. What is it that we can have? Now, what is it that we are going to have here? Now, we are going to have a possibility of a graph. So the graphs that we are going to have, it is either they are going to be a DC or an AC, or it can be, yes, AC or a DC. They're just the same. It doesn't matter what it is happening. But we need to talk to this about the position of the coil. Where is it? Where do we start? If we are starting there and when we are starting at 0 position, where is the position? And then let's talk to it. Let us also talk about the functions of each and every component that we are having. Things like brushes, it is to make contact with the external circuit. We need to talk to that. The slip rings, the split rings, it is the split rings to ensure single rotation or single dimensional rotation. So those are some of the things that we need. And then we also need to look at the calculations, especially with the AC. That is where we are having the RMS values coming in, and then we need to talk to that. And then that is basically what we have for the making then the structures, colleagues. We need to give them the structures. It is very important that we give the structures, and then out of those structures, then they can get the function and the name of each and every part that we are having. And then other than that, then we go to the second last, in fact, it is the last question, which we hope it is going to be the same like last year. Then it is going to be on photoelectric effect, and then the spectrum. Now, I want to start with the spectrum. Colleagues, with the spectrum, let us talk to them, even though it is 2 marks or so, but it is about absorption and it is about emission. With the emission, it means then they are being transformed from a high energy to a lower energy, and then light, it is going to be shown. Now, because it is going to be shown, hence we are saying it is going to emit light. Because it is emitting light, then it is going to be a emission spectrum. Whereas with the absorption spectrum, then something must be at least lower, so that the gas here, they're using a gas as that, then it is going to absorb some of the characteristic frequency, which is form of energy. And then from there, what is it that we are going to observe? We are going to observe a continuous spectrum with dark lines. So these two we need to look at, and that this is a typical multiple choice question or an explanation question, what it is going to happen. Now we go here with the photoelectric effect. With the photoelectric effect, then it is this equation that we need to talk to. Now we need to talk to this and then say Basically, that E, it is the energy of a photon. Now, the other thing about this energy, it is depending on this part here, that it is equaling to Planck's constant multiplied by the frequency. But this equation also can be in the form of h, which is a Planck's constant, multiplied by the speed of light and then divided by the lambda. So this one also, it is talking to that E, it is actually inversely proportional to the wavelength. Now, if this be the case, it's because these two are the constants. Now, if your wavelength, it is high, like in the rate, then it means it is going to be having a lower energy. Now, lower energy, it is also associated with a lower frequency. So rate will be having a lower frequency. So they must move from this one to that one with ease. And then also talk to the work function, and then also talk to the maximum kinetic energy. With this last part, colleagues, if the learners are not writing the max there, they are losing 1 mark for the formula. So that max, it should be there. The reason is that equation, it is coming direct from the data sheet. So they need to look at this. Now, in general, colleagues, when we approach questions with graphs, depending on the topic, what is it that it is there? If our learners are given any form of a graph, let us try by all means to look at what it is on the y-axis and what is it that it is on the x-axis. Now, after getting this, we are going to have these variables. Let's say, for instance, in this particular case, it is a graph where we are having a maximum kinetic energy here. It is along the x-axis, along the y-axis, maybe, for instance. And then maybe here across, we are having something like energy or frequency. Let me put it as a frequency. It is along the x-axis. And then they tend to give you this particular graph in this form. Now, what is it that it is happening? We are having this, it is along the y. We are having this frequency that it is changing. Now, this point here, it is a very important point, because at this point, we can see something is happening to the kinetic energy of this as the frequency it is increasing. So what is it that we need to look at? We know that this frequency, basically, it is having an effect on a particular equation. So what is it that we are taking? You have to take the whole of that equation, that E, the equation of E equaling to W naught. Maybe, for instance, W naught, we are just going to put it here, plus K. Now, what is it that should happen? Now, this is the equation, that is the original equation as we are having. This is the maxima that we are going to have. Now, it means this maximum, it is along the y-axis. Now, what does it tell us? We have to rearrange this equation such that at least we are left with K. So to be left with K, we are saying it is going to be K max here, right? Then it will be equaling to what when you go here? Then it is equaling to E, right? And then minus your work function. Now, importantly about this, it is this part here. We can write it as, just if you can see here, I end up with K equaling to E. Okay, I'm going to say plus into minus, sorry, my bracket, minus W naught. But this E, what is this E here? This E, actually, it is the energy of a photon, which is going to be HF. Now, our F, it is along the x-axis. You can see that it is along the x-axis. Here it was. here. This one, it is along the y. Now this is along the x. Now what is this here? It is on the negative side. The negative side, it is here. Meaning that this value here, it is actually our work function. Now, what is happening here? It is a frequency here along the x. Ne? Now, what is this? It means therefore that my k, it is a y. My frequency, it is going to be along the x. Now my plus will remain as a plus, but now this is going to be my c. That is where the graph, it is cutting the y-axis. And then my h, it is going to be my gradient. Now, that is a multiple choice type of a question or a long question where they will be asking you, what is the gradient here? The gradient of the graph. What is represented by the gradient of this graph? Then we can say that the gradient of this graph, then it is going to be there, the Planck's constant. Now, for each and every graph, we need to go this route, that we have to identify what is it that is on the x, what is it on the y, and then try to find an equation that it is going to talk to this. Then we are able to can say, now I have this equation, now I rewrite it, and then because it's a straight line, then I must strive to get a graph in the form of y equaling to ax plus c. And then the mx plus c, the m, it is going to be my gradient, and then everything, it is going to be the way it is. And then that is basically what we are having. Before I sign off, is there any other question or any other input? Ntate Lipita o teng kapo ke mme? Any question, batswadi? Ntate Nambane?
Thank you very much, Ntatentsiye, and I would like to just take this moment and say thank you very much, colleagues, for this initiative. I hope that our learners will basically get the information, but what I wanted to iterate more was I did record the session. It will be available on our YouTube channel immediately after this session for those that maybe will want to recap here and there, because in that NCA you did a very good job. However, somewhere I felt you were a little bit very fast for me. So that's the reason why now we need to have this recording. That is all that I wanted to say in that NCA. Thank you very much. We are hoping and looking forward to paper 2.
Thank you, Ntate Nambane. Next time I'll be a bit slower.
Thank you very
and not
much.
rush. But the time really, it was not on our side. 1 hour for the whole. It is not easy in that. It was not very easy.
Thank you,
And
sir.
colleagues, I know they want to give to the learners as much as they can. No, and also Ntate Nambane and colleagues, really, from my side, I want also to thank you heartily for the time that you took to be with us. And then it is always a great pleasure. And we look forward to meet you. And best luck to our learners, not your learners, our learners. We hope they will do the best out of the situation in which they are. Let them stay calm, and then the marks will be just be coming in. And then thank you very much, colleagues. Thank you. Thank you.
Masibonge baba.